Hello everyone. In this video, I'm going to give a brief introduction to how could we derive a finite discretization schemes. So generally speaking, there are two approaches. The first one is that we approximate the solution using the Taylor series expansion, or we derive the finite difference discretization scheme from the polynomial approximation. So in the first approach, as usual, if we have a solution like this curve, we need to define a fixed point where the function value f, we already know, for example, this point, call it xi, and we try to approximate the value in the neighborhood of it. So, for example, is here xi plus delta x. So, in Taylor series expansion, for example, we want to find the value at fxi plus delta x. It can be extended from the fixed point xi plus from the first derivative of fx xi times plus or minus delta x. It depends on the approximated point on the left-hand side or right-hand side of the fixed point. For example, if the approximated point is on the left-hand side, here, what we have is xi minus delta x. So you need to consider the plus or minus sign here. And you can write the third term as 1/2 second derivative of f at point I times plus or minus delta x squared. So we keep going with expansion into a certain order of derivative. Plus or minus delta x out of n. So, for example, we extend it into n plus p. At point I times plus or minus delta x power to the power of n plus p. So, if, for example, we want to find the derivative at xi plus delta x or to the power of n. So, for example, if we want to find the nth derivative of the function f at xi plus delta x, so this is the derivative I'm interested to find. So we need to find the nth order derivative of function f. And what we need is that we truncate until here. So the higher order term, we assume it to be an arrow, right in this way. And we define them as arrow. So we consider the right hand side, the power higher than n as arrow. So we call it p. So the whatever happens there is much smaller and has negligible influence to the accuracy on the left hand side. So when we get rid of the right hand side, we also need to cancel out the lower order term. Cancelled via computation. such that we can keep the nth order of derivative. So this is the concept of Taylor series expansion, and how we did that. For example, actually in Taylor series expansion, we consider each term as a mode, a numerical mode, to represent the true solution. For example, the first term here, it means that the value at fx plus delta x is equals to the fx at xi, so it's a horizontal line, is a constant solution. And the second term, the solution at fx plus delta x has a linear relationship with the solution at fxi, so it's a linear relationship. And the third term is a parabolic shape. So when we plot it out in the solution graph, what we are trying to do is that we use certain function and approximate from the xi. For example, the first mode is a constant solution. We elevate the solution from 0 to the level of xi. We call it bias in computational science. And the second mode is a linear relationship. So from the xi, we try to approximate linearly until the xi plus delta x. And the third mode is a polynomial shape. For example, we have a certain gradient is a non-constant gradient. So as we increase the order of derivative in the Taylor series expansion, including more terms, we're actually refining it until finally we get close enough to the true solution, and the error is negligible to us. So the second approach is through the polynomial approximation with certain order of the polynomial. So we assume that the solution of a partial differential equation can be approximate at certain order of polynomial in the polynomial form. So for example, we have 3 points here. The first, we assume we want to find the derivative, first order derivative at point P here in the middle. And we have the point W and point E. And the distance from P to W is delta x1. And the distance from P to E is delta x2. And so we assume the form, we assume it first. We assume the final form of the solution fx is a times bx plus cx squared plus a certain order of arrow we want to neglect. So any order higher than this one, we consider them as an arrow, because delta x is a small value here. Here delta x is small value. We try to approximate the solution not far away from the fixed one. So it's a small value. If we keep increasing the order of this small value, we times them multiple times, it becomes even smaller every time we time it with itself. So we can reasonably neglect a certain order, but how much we want to neglect it is so far is prescribed, depend on our requirement in the final finite difference equation. So let's say we want to keep and do the third order, so we truncate it from here. So for the solution at point W, we have fw equals to a minus b delta x1 plus c delta x1 squared. So this is the solution we approximate with this polynomial. And the second second point is fp. We know it's a. So because we take a local coordinate here, we say 0. So on the left hand side, we have negative delta x1. So for we, we have a plus b delta x2 plus c delta x2 squared. So for the coefficients a, b, c, those are the values we want to find from this equation system. So we want to solve for a, b, c. Once we solve this equation, this system of equation, what we get is a equals to fp, b equals to fe minus fp times delta x1 squared minus fw minus fp times delta x2 squared over delta x1 times delta x2 times delta x1 plus delta x2. C equals to fe minus fp times delta x1 plus fw minus fp delta x2 over delta x1 delta x2 delta x1 plus delta x2. So because we want to find the first derivative at point P, so based on this form, we will soon form a polynomial. What we know is that the first order derivative at point P equals to B. So B, we already get the value here. So this is the final form of the finite difference approximation of the first order derivative at point P here. This is the form. So basically, there are two ways to derive the finite difference discrimination schemes.